Good evening, everyone. Welcome back to NPTEL live session for week 3. And we'll be waiting for a few minutes for others to join. So in the last section, what we have seen that we come. In the last live session, we were mainly focusing on what is chirality, how chirality and symmetry can be related with each other, how to find out chirality, like which are the point groups which we can call as that they are chiral in nature. And also we saw all the symmetry elements, how to find out the point groups, how to find out that whether this is chiral or not, that also we saw. Then we saw its two isomers. So here we got to know that the chiral point groups, they generally belong to either CN or DN. They should not be having improper axis of rotation symmetry element. Then we also talked about that how to find out the point groups. So that was I will just give you a brief. So firstly, we need to check whether the molecule is linear. If it is yes, then it goes to two categories, whether it is having inversion center. If it says yes, then it's D infinity H. If it says no, then it's C infinity V. That comes under linear molecules. Say if the molecule is not linear, then we need to see whether it is cubic. We need to see whether some special symmetry groups are present or they are having the maximum number of symmetry elements, then they come under this category. And after that, if this is a no, then we need to see whether Cn is there or not, where n is greater than 2. If the answer is no, then we will see whether sigma is present. If answer is yes, then it is called as CS point group. If answer is no, then we need to see whether inversion center is there or not. If it is yes, then it is CI. If it is no, so we started with is there any proper axis of rotation? The answer was no. After that, sigma was no. Then I is also not present. So what else is left? That is only a C1. So these three are called non-rotational groups that we have already discussed in the last class. Now, if we have Cn, then the next question, do we have n C2s perpendicular to this Cn? Say, for example, if C3 is the main axis, whether three C2s are there or not. And if the answer is no, then see whether it is having sigma h. If answer is yes, then it is C NH. If the answer is no, then check whether it is having sigma D or sigma V. If answer is yes, then it is C NV. Answer is no, then it is just Cn. These are called single axis rotation groups. After that, if the answer is yes, then the again question would be whether it is having sigma h, then it becomes DNH. If it is having sigma D or sigma D, then it becomes DND. And if it is having nothing, then it is DN. So these are dihedral groups. So this what we read in the last live session, how to find out the point group, and that is very important to understand. Then we went ahead and we discussed some problems. And in the last session, since we talked about tetrahedral point group and we discussed its all the elements, which is very important. And I told you guys to go back and check for the octahedral symmetry also. So now we will take up first the octahedral symmetry. Then the three questions that was left in last session that you guys were supposed to solve, that we will take up into picture. And then we will be having a discussion of some concepts that we talked in the week 3 related to the chirality and biology. So firstly, if we see, so here we are talking about that we need to find out. So this whole is your total number of symmetry elements, which gives you a point, which gives you the order of the group as 48. For the tetrahedral, it was 24. For octahedral, it is 48. And we need to find out how the 48 is coming. In last class, we saw that 24, how we are getting the 24. So before that, we need to understand how octahedral symmetry looks like. So if we'll take this, So here, if I will just name them, it is A, this is B, this is C, this is D, upper one is E, and this is F. Now, in octahedron, we know that vertices is equals to 6, and if we want to name them, they will be A, B, C, D, E, and F. Now, how many faces are there? Faces are 8. And what are the faces? Now, if you will see clearly, the left face, the one which I have highlighted in yellow. So the left face becomes A, E, D. Also, we have one more left face, which is this ADF, which is being drawn as green. Then we have, these are left faces because they are at the left side. And now, similarly, we will see which ones are the uh, right faces. So this blue in color, that EBC, EVC, and one more BCF, they are the right faces. This one also. Now, there would be two front faces and two back faces. Similarly, I will show you here one. So, for example, this is the front face, which is called as ECD, and the inverted one, A, and the inverted one, this DCF. This one. So these two are the front. And if we have to draw the back one, that would be this AEB and ABF. So these are front ones, and the back ones would be, back faces are A, B, E, and ABF. So this is what we found, that okay, 8 faces are there. Now the turn is of edges, and edges are 12 in number. We need to name them. So edges, and you know that key, it will be having these two connections, this connection to this vertex connection. So I will start naming it from A, AE, AB, AF, AD. So these are the things. Then I'll choose BC, BF, BA, we have already taken, BE. Now see the C1, CE, CD, and the last one is Just a second. DE. CB have taken. CE. CD. CF. DE. DF. CD. ED. Then EA taken. EB has been taken. EC taken. ED taken. And F. FA. FB. FC. FC. FD. Yeah, now it is completed. So in this way, we got that vertices, faces, and edges. Now, as I've already mentioned here, what will be the locations from where you will be having your symmetry element and what is the number of symmetry operations? That is the flowchart that we have already given. But to understand it properly, we will just see that in this molecule, in this symmetry, what would be the maximum n value for the proper axis of rotation? So since it is having 6 vertices, so is C6 is possible? No, because that 60-degree rotation will not be able to give you the equivalent orientation. So then we have to see whether below than that anything else is possible. So we will just check C4, and C4 will pass through the opposite vertices. Here it is written that C4 will pass through your opposite vertices. So say for example, this one and this one is my one vertex. So here, or if you're taking like this one and this one. So these two vertices are there. And if I will be having to the opposite vertices, if I'll be having a C4, and if I'll rotate it by 90-degree rotations, I will be getting a 90-degree. So say for example, if this is my z-axis, and corresponding to that, this is one more, this particular way, like y, and this particular way, x. So now you can see so we are having 3 C4s in 3 axes. We can consider, so say for example, this is x, this is y, and this is z. So these are all 90 degrees perpendicular to each other. So 3 C4s are there. And we have already seen that C4 can give you C4-1, C4-2, C4-3, because C4 4 times will be equal to E. So only these 3 rotational operations would be considered. Therefore, one C4 is giving you 3 symmetry operations. So 3 C4s will be giving you 3 into 3, that is 9 symmetry operations. Now coming back to along the C4, we will be having S4 also, which is fine. You know that S4 also will give you S4 1 and S4 3 only, because S4 2 and S4 4, it is not an improper axis of rotation. So this is also clear. Now after C4, we need to see whether C2s are there or not. So it is saying that it is passing through edge centers. So opposite edge centers, here it would be O. So here now we are having, this is one edge, this is one edge, this is second edge, and here now we are having one C2 where it can rotate by 180 degrees, and this would be flipping. Similarly, if I'll take this one, it would be having here, here, and since we are having 12 edges, so opposite edges that centers, they will give you a 6 C2. So you will be having 6 C2, and we know that 1 C2 gives only one operation. So since we have 6 C2, that is also give you going to 6 operations. Now, to find out where would be the inversion center. So if I'm drawing here a metal, this is L, ligand, having an octahedral symmetry. So if this is my center point, and if I'm going to right side and to left side, at equal distance, I'm getting the same thing, which is possible in every direction. So I'm getting here L, here L, here L. So inversion center is lying at the midpoint, and it is existing. Now we need to see, besides C4, C2, we need to see that whether we have C3 or not. Since we already know that we saw C3 could be possible because it would be having a triangular faces like this way. So these 3 vertices are making one triangle. This is making another triangle, and so on and so forth. So when we are applying C3 to it, they will give us an equivalent conformation. So C3 will be passing through the opposite triangular face centers. So this is, if suppose this is one face and the inverted one is the dark. So the center of these, in between these two, whatever is the center, and if the axis is passing to that, so there would be a rotation of C3, like 1, 2, and 3 will be rotated among themselves. 4, 5, 6 will be rotated among themselves by 120 degree, and therefore they will retain their equivalent conformation. So therefore C3 is present, and since we know that C3 gives you 2 operations, and since there are 4 C3s, because we have 8, we need to just see in that manner, 8 faces. So opposite face centers, there would be 4 in number, corresponding to that 4 C3s, and each C3 gives you 2 operations. So 4 into 2, it's 8. So there would be 8 C3. Now along, as we saw that along C4, we were having S4. Now along C3, whether S3 would be existing or S6. S3 is not possible. So S6 we will see. So since S6 will give you two operations, S61, S65, and since four C3s are there, four S6 would be there, which implies 4 into 2, that is 8 operations. So S6 is along your C3. After that, we need to find out how many number of plane of reflections are there. So firstly, we saw that C4s were along the 3 axes. So along each axis, we would be having a sigma h perpendicular to that, like one sigma h perpendicular to one axis. So therefore, there would be 3 sigma h, and each sigma h gives one operation. There would be 3 operations of sigma h. Then we saw that since 6 C2s are there, that is reflecting, there could be 6 sigma V. But these sigma V's, they are actually the sigma D's, because that is bisecting two vertices and reflecting 4 vertices. So since we said that C2s are existing in between the centers opposite vertices, passing through that there would be one C2. But the plane is actually cutting the two C2s, where it is bisecting the two vertices and reflecting the 4 vertices. So therefore, we are having 6 sigma Ds. So ultimately, in total, we are having identity 9C4, which can be written as 6C4 plus 3C2, which is equal to C42 plus 8C3, 6C2, 6S4, 6 sigma D, I, 8S6, 3 sigma H, 6 sigma D. So this, if you will count, that will come as a 40. So I hope you guys have understood this. Now, we will take up the questions from the last class that was not being able to cover. So since we were asking about, we said that there is a condition that chirality happens when there is no SN present. Or we can say the point group should belong to Cn and Dn. They could be called as chiral. Now, firstly, we know that H2O2 stays in 3 forms. One is cis, one is trans, and another is open group. We have discussed in details in the last live sessions. So cis is having, I'm not drawing the structure again. You can go back and check it. It's C2V, it's C2H. And we need to find out the point group of first this open group. So if consider it as this. So if I'm having oxygen-oxygen bond here, 1H would be here, 1H would be here. So it is having a point group of C2. Since it is having a point group of C2, it belongs to Cn category. So logically, it should be chiral. But if you see carefully, that this single bond, oxygen-oxygen single bond, or any single bond for that matter, they are highly flexible for bond rotation. So when the bond rotation happens, and that will be having something like this way. So if I am drawing its mirror image, thinking of it that it is a chiral molecule, so the mirror image would be like this way. But since the bond rotation is happening, it will again come back to this original form. So therefore, no chirality at all, because both the images will then become superimposable. Therefore, it has to be remembered that H2O2 open book form, even though it belongs to CN category, still it is not chiral because of the reason being bond rotation, single bond rotation. So I hope you guys have understood this. Then the next question of the last session was that whether this complex where metal is bound with the bidentate ligand, ethylene diamine, I've already shown you the structure of it, that CH2, CH2, NH2, NH2. So the binding sites are the nitrogen with the lone pairs, and they bind with the metal. So here, firstly, we have to draw the structure, and I am taking it as a NN. So I'm not drawing the full form. So N. So if you will see that, is it chiral or not? So for chirality, we need to find out its point group, whether it belongs to CN or DN or not. So if you will see clearly that it does have a C3 axis, if we'll make a triangle. So C3 is existing. Now the question is whether three C2s are there to make it a DN group or not. So if you will see clearly, C2s are also there, which are passing like this bond. C2s are there. So C3 is there, three C2s are there, and no plane is there. Therefore, it is having D3 point group. And since it is Z3, therefore it is a chiral molecule. When we have a chiral molecule, then it would be having a lambda and delta isomers. So this is from the last live session. And the last question was how many number of C2 axes are present in CCl4? If you will remember, if you remember clearly that we discussed the tetrahedral symmetry in details, and we know that how many C2s are present in your, so there are three C2s. So since C, Cl, Cl, so it belongs to a tetrahedral symmetry. Symmetry also is tetrahedral, so that is fine. And since it is there, and we know that it passes through opposite edges, and we have 3 C2s in number. So here we are having four vertices, four faces, 6 edges, which are connecting these two. So the highlighted with the blue ones, they are the 6 edges. And if I'll take one edge and here, and if that opposite center I'm taking, so it will invert, it will have that C2 over there, 180-degree rotation. So 6 edges means 3 opposite centers will be there, and therefore 3 C2s. So this question is also done. So these are very important things to find out the point groups, to find out the chiral, whether the point group is a chiral molecule is being a chiral or not. That we can simply look from the point group. So I hope you have understood it well. Now we will talk about the weak 3, that is a relation between the chirality and your, sorry, and biology. They're not going to go into the full details, but that Professor has well